Okay, no questions? Uh-huh.
So we're finishing the unknown this week.
Yes. Yeah, you're gonna finish the unknown this week.
If we need more time, so we come in the morning lab.
Right. If you do need more time, today I'm going to talk at the beginning of lab, but Thursday I'm not going to talk at all. We'll have the full 3 hours on Thursday. But if you do need more time, come into the morning lab. The morning lab meets from 9:30 to 12:30, and so you're welcome to come in there. Okay, any other questions? No, I need to finish up this problem we were talking about last time. Excuse me, which is the phosphate. But let me go back a little bit. If we're dealing with phosphoric acid is a triprotic acid, right? The triprotic acid is going to have 3 K values. Ka1, H3PO4 plus water. This is going to yield hydronium plus dihydrogen phosphate. The dihydrogen phosphate that's produced, this is what we call Ka1. The dihydrogen phosphate that's produced can also lose a proton. So the dihydrogen phosphate plus water, liquid, is going to form hydronium plus monohydrogen phosphate. This is Ka2. And so Ka2 just represents the second proton of phosphoric acid coming off. And the third and final proton, we'll see in HPO4 2 minus, monohydrogen phosphate, plus H2O liquid. This yields hydronium plus phosphate. And this is Ka3. And so we would do these steps, Ka1, Ka2, Ka3, and then Kw as a potential fourth step. But when we're dealing with something like sodium phosphate, we aren't dealing with phosphoric acid in the Ka equations. We're dealing with the Kb equations. So there's a question about what this comes from. And so when we look at phosphate itself, phosphate we call a tribasic base. It's a tribasic base because it's capable of accepting a total of 3 protons. And so altogether we can put 3 protons on there. And the steps would be like this. Phosphate plus water. This is going to give us monohydrogen phosphate and hydroxide. This we call Kb1. And we figured out what Kb1 is. Kb1 was Kw over the Ka of its conjugate acid, which was HPO4 2 minus. So I'm backing up a little bit because I didn't cover this. I'll just jump straight into it. But it's capable of accepting 3 protons. So the next thing is the monohydrogen phosphate can accept a proton from water. This is going to form dihydrogen phosphate and hydroxide. So this will be Kb2, which is Kw over Ka for dihydrogen phosphate. What were the numbers here that we calculated? What was Kb1? 0.0238, was it? Somebody have it, or do I have to calculate? Rather not have to calculate it. Let me just tell you. When I do the problems on the board, you should try to repeat them. Or at least the calculations. We didn't quite finish this, but you could have repeated the calculations up to step 2. Well, that's always a good thing to do because then you can see, where any mistakes made, or you can see if you'll run into any hitches. And so, like, you should repeat the calculations for the kV. Did you get the same number? You know, that kind of stuff. Maybe you did the calculation in class. But did anybody write down the numbers? So I don't have to do it over again? KV1? No. Uh-huh. 0.0238. The KV2 for HPO42 minus?
1.59 times 10 to the negative 10.
Did you round this? Was it 1.59 or 1.58? 1.58 times 10 to the negative 9? No, 7. Okay, how do these relate? Well, Kas are totally different. You know, the Ka for phosphoric acid, just get, you know, we had it written down earlier, but let me just get that for you here. 7.1 times 10 to the minus 3. The Ka2 for phosphoric acid, 6.3 times 10 to the minus 8. And the Ka3 is 4.2 times 10 to the minus 13. But we aren't doing the Kas. We're doing the Kbs because we do the Kas if we had phosphoric acid. You know? But since we have sodium phosphate, we're doing Kbs. Because sodium phosphate's a base, right? And so here we go with this. The final proton that this can get is H2PO4 minus plus another water, H2O liquid. This is going to produce H3PO4 plus hydroxide. This is Kv3. Kv3 I don't think we calculated. It's going to be Kw over the Ka for phosphoric acid. So we can calculate that right now. And so Ka is 1 times 10 to the negative 14 divided by Ka for phosphoric acid, which is 7.1 times 10 to the minus 3. I get 1.408 times 10 to the minus 12. And those are pretty weak as far as a base goes. What would be Kv3? And so, you know, this is an acid solution. An acid solution, what do we look for? You know, if we have an acid solution, you're going to look for all the, what? This is just a review from yesterday. But ideally, you guys should be reviewing these, you know, every day. Try not to wait for the night before the test to cram.
Why did you use the Ka1 instead of the Ka3 for the third one?
So the question is, this is Kb3, so why didn't we use Ka3? I'll tell you on the test, lots of people do that. They'll see Kb3, they'll use Ka3. But it's wrong, I marked it wrong. Maybe about 10%, 5 to 10% of the students will do that. It's wrong because the relationship between Ka and Kb, Ka times Kb is equal to KW only if, is this in your notes? I wrote it on the board yesterday.
They're conjugates.
Only if they're conjugates. If we use Ka3 here, Ka3 is for monohydrogen phosphate. Monohydrogen phosphate and dihydrogen phosphate are conjugates, but in the wrong sense. If we use Ka3, which is for monohydrogen phosphate, that is the conjugate base of this, not the conjugate acid of this. And so it has to be the conjugate acid of this. This is where you have to go back to, go back to chapter 5 and look at the conjugate relationships thing. I think is the best. Or chapter 14. They have to be conjugates and they have to be acid-base pairs. This is especially tricky because we have lots of conjugate relationships because we have amphoteric species. And so it turns out, well, dihydrogen phosphate can both be an acid and it can be a base. Therefore, dihydrogen phosphate is going to have a conjugate acid as well as a conjugate base. And so if you did Ka3, then what we're doing is we're getting the conjugate acid of this this is supposed to be, the conjugate base of this base. And so it doesn't match. The conjugate pairs don't hold up. And so if we're calling this a base, H2 PO4 minus is a base, then the acid has got to be H3 PO4. And so did you write any kind of take-home message from yesterday's thing? For acid, if you have an acid solution, what do you do? Well, I wrote it on the board, but me writing it on the board, people don't remember. It's you who comes up with the is better. It's easier to remember.
On the test, are we given this part, the left, or do we just know that off that?
On the test, you aren't given that part on the left. On the test, you're just given the numbers. On the test, you aren't going to have this. You're going to have that. And so you'll have H3PO4 and these three numbers. That's what you'll have on a test. Uh-huh.
For spaces, it's more consistent with reaction to generate oxides.
Right, good. And so for bases, we only do the KBs, right? For base solutions, just KBs, and also KW generates hydroxide, and we do it in order. KW is 10 to the minus 14, so looking at it, we do KB1 first, KB2. Now KB3 is 10 to the minus 12, which is still, it's pretty small, but it's still bigger than KW. And so the order of the sequence would be KB1, KB2, KB3, then KW. Sometimes it happens that KW is bigger than KB3. If KW is bigger than KB3, we do it in this sequence: KB1, KB2, KW, and then KB3, because KB3 should produce the least amount of hydroxide. We just go in order of Ks. Sometimes KW is bigger than KB2. We'll throw it up there. It's just in that sequence there. This is very tricky, and only a part of the class figures it out. For acid solutions, what do you look at? For acid solutions, you look at, I sense trouble for the next test. It's coming up. But there's still time, there's still time to study, I think. You want to start studying sooner. For acids, you want to look at the hydronium. Since there isn't that much time, there's a lot of time for the 15, but the 16 is going to be more compressed as is the other ones. So you look for the hydronium ion. And so if we have an acid solution, this is an acid solution, this is a base solution. And then there's one more hydronium producer, that's KW. Here it's close, you know. K3 is only 10 to the minus 13, KW is 10 to the minus 14. This is very close, you know, in terms of magnitude. But still, again, we'd do 1, 2, 3, then KW for steps, 4 steps. Now, do you have this down? Okay. What do you do with something like this? Let's say I had a solution of sodium dihydrogen phosphate. And so this is going to consist of the hydrogen phosphate. Do I treat hydrogen phosphate as a diprotic acid? Or do I treat dihydrogen phosphate as a monobasic base? In other words, should I do Kas for dihydrogen phosphate? This is sodium dihydrogen. Should I treat that as an acid? Or should I treat that as a base? Here it's easy, you know, because this cannot be acid. This is just base. And as well as this is very easy too. This is just acid. But dihydrogen phosphate is not easy because dihydrogen phosphate is both an acid and a base. So since it's both an acid and a base, what should we do? Should we do this or should we do that? What should we do? The Ka or the Kb? This could be monohydrogen phosphate. Or how about this? Sodium monohydrogen phosphate. What should we do? Treat it as an acid and just look for the Kas, treat it as a base and just look for the Kbs, or neither of the above? Yeah, actually, you have to do both. And so for amphoteric species like this, must do both. And so the easiest thing is we're going to put this off, you know. We're going to put this off until chapter 17. And so that means this last part of chapter 16, which deals with the ions as acids and bases, is tricky. And so let's, actually I didn't finish. Did I finish that phosphate? Did we finish that one? Do you guys want to finish it at home? Or do you want to finish it now? Do you think you could finish it at home? No. All right. Before I start talking about the ions, let's go on to continue on with this problem. Where did we leave off at? Step 2? Did we finish step 2? All right, step 2 was the monohydrogen phosphate plus water. This is going to give us hydronium. No, not hydronium. You see, this can go either way, right? This could produce hydronium or it could produce hydroxide. In this case, we want it to produce hydroxide. So it's going to go H2PO4 minus plus hydroxide. Why not hydronium? No, this is just a repeat. Why not hydronium? Because it's a base solution. In base solutions, we only look for the hydroxide ion producers, Kb. And so what was the equilibrium we got from this? Did we figure out the equilibrium concentrations already? Or not yet? What were the equilibrium concentrations?
H for the HPO4 minus it was 0.038299. The next one was 1.58 times 10⁻⁶. thing as the HPO4 2 No, so the mono hydrogen phosphate.
0.038. 0.038
Oh, 0.038
3
00
158.
Yeah.
Did we already check it?
Yeah.
The K, it checked out? Did this perturb step 1? No? Okay, now we're ready to go to step 3. For step 3, we have the dihydrogen phosphate now. Dihydrogen phosphate is going to hydrolyze water to produce what? Do you see how easy it is to get mixed up? This is why I wrote the Ka. I wrote the Kas on the left side because a lot of people do this on the test too. They'll hydrolyze this to form hydronium plus monohydrogen phosphate. But we aren't going to do that. Well, what are we going to form? We're going to form what?
Phosphoric acid,
Phosphoric acid
hydroxide.
and hydroxide. So that last equation there. There aren't that many of these types of problems around. So you gotta watch out. A lot of people get this mixed up with phosphoric acid. This is not phosphoric acid. We aren't doing Kas. All right, tell me what the initials are. Actually, why don't you go ahead and complete this ice table for me, all right? And then I'll come back and check it.